Is my slide is visible to you, students?
Yes, ma'am. Yes.
Thank you. So let me start. Today's session is about Huffman encoding trees. Huffman encoding. So encoding, decoding. Oh, what is that coding, isn't it? So before
Excuse
going to this, hello.
Am I audible, ma'am?
Yeah, you're audible.
Ma'am, I think we were doing something like binary tree, I guess. So you were telling about the insertion and something adjoint tree. Not over, ma'am.
I'm not understanding what is your question. Oh, you are telling answer, right? Something you are telling about the Huffman encoding. Hello.
Yeah. Okay,
I think your voice is breaking. Your voice is breaking, Priya. Okay. So let us start. So encoding, decoding is very, very important when you are saving some information in a computer. For example, there are codes available like ASCII. You can hear me, right? Students, can you hear me?
Yes, ma'am.
Okay. So, in order to proceed about Huffman encoding, I would like to just touch upon some of the encoding techniques. One is ASCII coding. ASCII is nothing but American Standard Code for Information Interchange. And this ASCII is useful whenever you want to store something in a computer, then all the character will be stored in the ASCII format, isn't it? So do you know how many digits will be used for representing each and every character in ASCII?
7 bits.
Seven bits. Yes. So another encoding scheme or coding scheme is EBCDIC. EBCDIC, which was used in IBM mainframe and IBM mid-range computers for storing the data. And EBCDIC, in which each and every character will be saved in the 8-bit format. Okay, so now how to represent the data in the computer? There are many coding schemes available. Okay, and also you want to communicate some data, so the data will be encoded and then in the receiver side it will be decoded, right? So for handling the secret messages also the encoding and decoding schemes are useful. So now let us look at some of the coding schemes. There are two major types available. One is fixed length coding and variable length coding. Fixed length coding and variable length coding. If you look at this particular slide, we have considered in my language. In my language, I will be using the characters A, B, C, D, E, F, G, H. So there are only 8 symbols available, A to H. Okay, so I want to represent a message by using these symbols. So what I will be doing is I will be encoding this message using some encoding technique, right? So consider in this particular example, A is represented as 001, B is with 00, A is by 0000 and B is by 001 and then 010, etc., and H 111. So by using this coding method, how to represent this message? The message is BACADAEA like that. This is a message. How to encode this message? Okay, using this convention. This is actually, you can assign some binary pattern to each and every symbol. That is fine. Considering the symbols and the corresponding pattern, how to represent this message. Okay, so what you will do, you will go for the first character B, and what is the equivalent code? 001. So you will write 001. Then A, it is 000. So you will have a table. In the table, you will have symbol and the corresponding bit patterns. And when you want to write some message, for each character in your message, you will look up the table and then fetch the corresponding pattern, and then you will write it as a lengthy string, isn't it? So now this is pixel length coding. What is meant by pixel length coding? For each and every symbol in my language, I'm going to assign a bit pattern of same length, So in this case, I have used a bit pattern of length 3. Okay, so this is one of the example. Considering in my language, I will use always the symbols from A to H, so that and for each and every symbol, I have the equivalent 3-digit binary number. And when I am writing the message, I will be referring the table and pick up the corresponding bit pattern for each and every character, and then I will write a bigger bit string. So in the communication, you will use this bigger bit string for representing your message. Okay, so this is what pixel length coding. And let us talk about variable length coding. What is variable length coding? And take this example. A is represented by 0 and B is by 100. So, and C by 1010. If you look at this one, for A, I'm going to use a single bit, and for B, I'm using 3 bits, right? And for C, 4, and for D, 4. So, if you look at this, different symbol is represented by different length coding, isn't it? So now I want to represent the same message for the same message, and if I am using the variable length coding scheme, then your message, your bit length will be like this, right? Your bit string will be like this. If you compare this string and with this string, you can see this bit string is lengthier than this string, right? So in the pixel length string, in this particular scheme, the disadvantages. Actually, I'm just comparing the pixel length coding and the variable length coding. So what is the disadvantage of pixel length coding? What is the advantage of variable length coding? So if I say what is the advantage of variable length coding, we can save some space. Right? We are making it as a space efficient. For example, another thing is we can fastly send the data in terms of communication. So when I want to send this particular string as well as this one, this second string will be taking a less time, and also it will take less space. Okay, so we can save space when we are using variable length coding in our application. Okay, so we are talking about encoding scheme. Encoding is nothing but for each and every symbol, we will be representing it in the form of zeros and ones in a binary terms. Okay, with some fixed length or with a variable length. Okay. So now this is the drawback. The drawback is it will consume space. The pixel length coding will consume much space. So how to solve this problem? So if you look at one of the code, the very famous code, Morse code. Morse code was used in the earlier days for fax and all, doing, you know about fax machine, right? And faxing. And this is also a coding method, Morse code. The Morse code, if you look at the content, the symbols are nothing but dot and dashes. Each and every character will be represented by the combination of dots and dashes. But if you look at the pattern, the length of the binary pattern for each symbol will be different. This is one of the example for variable length code. Okay, so the Morse code by which we can represent each and every character in terms of dots and dashes, but with different count. For example, the letter E can be represented by a single dot. And if you take some X, the letter X can be represented by dot, dash, dot, dot. Okay, example. So now, if you in the Morse code, what you are following is a variable length code. The variable length code is framed in the concept of, for example, in the English language, E is the character which will be often used, right? E, if you just write, you just see the slide itself, E will be occurring more number of times. So if any character is occurring more number of times, that will be represented by smaller length binary code. So that here in the Morse code, they are using a single dot for representing the symbol E. E is the most occurring symbol in English language. Okay. So now here, when you are representing, say like this, it's a sequence of bits, right? Here, it is a sequence of bits. Now we want to know where the symbol ends. When in the destination side, when they are decoding it, they have to know where the symbol ends. Okay, so you have to know the scheme. The destination has to know the scheme, and each character is represented by how many number of digits. In the fixed length coding scheme, we can specify, we can tell to the destination party that each character is represented by 3 bits. But in the case of a variable length coding, how to represent, because each and every symbol is of different length. See, in this case, A with a single digit, B is 3 digit, and C is 4 digits. So where the symbol ends, there is no way to know, isn't it? So, but if you look at the Morse code follows, the thing is, it uses the pass. It uses pass. That means E is a dot, and leave just pass. That means some spaces, and then another character starts. So we must have a what is that? We in some way we have to mention the end of the symbol if we are going for variable length encoding, isn't it? So another way is we can also go for the prefix, that is prefix code. What is meant by prefix code? That is, I say that A will start with 0, B will be starting with 100, like that. So by knowing this prefix, by creating some prefix pattern, and the destination may be understanding where the symbol ends, where the symbol starts. In this case, if you have a prefix code, where the next symbol starts. So the 0, if any symbol is starting with a 0, it is A. If you are while reading the string, binary string, and if you find a pattern 100, it is starting of B, it is B. Okay, so these prefixes are not used for any other symbol. Okay, so we are not going in detail. So I'm just giving you the introduction about the variable length coding and Morse code, etc., etc. What are the different types of coding schemes available? Okay, so now, so this is the solution is you can use the prefix for each and every symbol so that the destination may be understanding where the next symbol starts. Okay, so this is in the case of variable length encoding. So now let's move on to the Huffman coding. What is meant by Huffman coding? How to represent it? It can be represented as a binary tree. So binary tree in the sense you will have a left child, you will have a right child. And in a tree, you will have a leaf node and you will also have a non-leaf node. The non-leaf nodes are called as a non-terminal nodes, right? So now we are going to represent the what is that? The message in the form of a Huffman code. That Huffman code is nothing but treated as a binary tree. We are representing the whole information in the form of a binary tree. Okay, so how it will look like? What are the information you will say at each and every node? Okay, at each and every node, you will have a symbol and also the associated weight. What is meant by weight? Okay, what I am saying is in the binary node, binary tree is nothing but a collection of nodes, and in each node, the symbol associated with that position and also the frequency. The frequency is called as a weight. Okay, I can also say it is nothing but a relative frequency. What is meant by relative frequency? That means if you take this particular string okay, and a symbol with reference to here, okay, I take this text. With reference to this particular message, A is occurring how many times? G is occurring how many times? This is called as a relative frequency. In the given message, paragraph or a word or whatever, how many times the symbol is occurring in the given string, given message. Okay, that is what a relative frequency. That relative frequency, we are calling it as a weight. Okay, so if you look at any node, the node will have a symbol as well as the weight, the frequency, how many times it is occurring in the given message. Okay, so this is for the leaf nodes. In the case of a non-leaf node, okay, in the case of a non-leaf node, the non-leaf node contains a weight, that is sum of all the weights of the leaves lying below it. For example, a parent has left child and a right child, and for the left child you assign the symbol and weight, and for the right child you assign the symbol and weight, and you add both weights and put it in the parent node. Okay, so this is a concept, this is the overall concept, and the weights are not used when you are doing a process of encoding and decoding. This is an important point you have to know. Let me show you a Huffman tree. Huffman tree, you just see, this is one of the example. So this is a binary tree. At any point you can see there are two children for any parent node. Okay, and you look at the leaf node, the leaf nodes are here. A is the leaf node, isn't it? And B is a leaf node, C is a leaf node, and for the leaf node there is a weight. So what is that weight? Weight is nothing but the frequency. Okay, so B is occurring 3 times, C is occurring 1 time, D is occurring 1 time, E is 1 time, F is 1 time, like that. Now, if you look at the parent, you consider C, the parent of C and D, what is that? The symbol is the combination C and D, okay, and then add the weight, 1 plus 1, it is 2. Okay, look at this one, this parent for left one, what you have BCD, so BCD, and the right one EFGH, so EFGH you are adding it, and what is the weight? 5 plus 4, it is 9. Okay, so now so you can just given the message, you can able to generate or create a Huffman tree like this, isn't it? So whenever actually you have to start with the root node. This root node, well, when you are creating a tree, you cannot start with the root node, but you have to go from the bottom to top, isn't it? That is possible. You will create a leaf node and then the parent and then the parent, and slowly you will come up with the root node. That is possible. Okay, so this is one structure of a Huffman tree. So now, after generating a Huffman tree, okay, how to generate a Huffman tree, I tell you at the end. After generating a Huffman tree, I would like to perform encoding process. So how to perform encoding process? Okay, so now there is a procedure. Okay, so for example, what is meant by encoding? As I told that for each and every symbol, you will have a corresponding bit pattern. How to get that bit pattern? Okay, so that is what we are going to do. So now what we have to do is, first of all, you start with the root node. Go to the root node and move down until you reach the leaf node that holds the symbol. For example, here I want to write I want to represent DGH. I want to represent a message DGH. Okay, D is the symbol, G is the symbol, and H is the symbol. What is the equivalent binary pattern you will represent for DGH? Okay, so I want to have a message with DGH. So what is the equivalent bit pattern for this? Let us look at. Now, for each and every symbol, start from the root node and just go to that just to go to that node. So D, if you look at D here, what is the path? What is the path? So the root node, and then you're not moving left, you have to move right, okay? And then what? You have to move left, and then right, and then right, isn't it? So whenever you are moving left side, you just add 0 to your code. When you are moving right side, you add 1 to it. Okay, 0 is for left side movement and 1 is for right side movement. So now I want to get a code for D. So what is the code? Can you tell me? Start from the root node. You have to go to right. If it is right, what? You have to put 1 in your code. So 1 and then go to the left. 0, then right 1, another right 1. So you are just reaching D. You are just reaching D. So what is the encoding you will use for representing D?
1011.
1011. Yes, yes. So 1 0 and then 1 1. So likewise for G, you have to go to right, 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 and then left. So 1 1 1 0. And for H, 1 1 1 and 1. Okay, so this is the way you have to find out the equivalent bit pattern for each and every symbol. This is for encoding process. Okay, so given an input, what is the input? A bigger message. The message consists of consecutive characters. So you have to take each symbol one at a time and then refer the tree starting with the root node and then reach the node by moving left or right. Okay, when you move left, put 0. When you move right side, you put 1. Okay. Okay, so just I would like to know from you how to represent F according to this tree. Anyone of you? How to represent F? Start from root node, right side, left, right. So what is the encoding bit pattern?
1101.
1101, that's all. So now this is encoding process. How to decode? How to decode? So now the input is nothing but a bit pattern, some sequence of bits. Consider in this case 1001010. This is the input. Now we have to find out the reverse. What are the symbols transmitted, or what are the symbols represented by this? Okay, so what we need to do is the reverse case. You just read the first bit, but before that you should be in the root node. So what is the first bit? It is 1, so you have to move right, and then 0, you have to move to the left, and then another 0. Another 0 is what? You are just reaching a leaf node. What is the leaf node symbol? The leaf node symbol is what? Now you reach the leaf node, isn't it? Hello students, you are starting with the root node. Just read the first character. What is that? It is 1. So 1 means what? You have to move to the right. And what is the next character? It is 0. And another character? 0. So I'm just moving on the left side only. Now I reach the terminal node. So what is the character here? B. It is B. Okay. So you have to encode in your output B you are writing. And then what is the next character? So once you are reaching the terminal node, go to the root node once again. So you are now in a root node. What is the next data? It is 0. 0 means what? It is left side. From the root node, left side. What is that? You reach a terminal node. It is A. So the encoding second character is A. And then go to the root node, and then it is 1. So right side, and then 0 left side, and then the right side, and then the left side. So you will reach C, isn't it? So what is the symbol? B, A, C, isn't it? So this is the way you have to decode the data. So for decoding, assuming the Huffman tree is available and the input bit pattern is available, you are going to find out the symbols, equivalent symbols. This is the way. So what you have to do, you just move to the root node, read the first character. If it is 1, go to the right side. If it is 0, go to the left side and continue the process till you are reaching the leaf node. If you are reaching the leaf node and in that node, what is the symbol? You just write it. Okay. Once you are writing in the output, then you have to move back to the root node and continue the process. Okay. This is what decoding. Now let us look at how to generate or construct the Huffman tree. How to generate or construct the Huffman tree. So what is the idea behind it? What is the logic we have to follow? Okay, so the idea is to arrange the symbols in the tree. Okay, the symbol with the lowest frequency will appear farthest away from the root. That is, the lowest frequency symbols will be in the lowest, or it will be in the depth of the tree. It is very further away from the root. Okay, this is the idea. So why this idea? How come it is going to help us? How come it is going to help us? Because whenever you are take a decoding process, when you are reading the data from the message, you have to move this side, that side, etc. And now some of the symbols are mostly occurring. So if it is occurring in the middle of the tree or in the initial stage or near to the root node, we can just wind up, isn't it? So this is for saving time. This is for saving time. Okay. But now here, make a note that we are not going to generate an optimized Huffman tree. Okay, just a Huffman tree. It is not optimized. Whether it is optimized or not, we are not going to check it out. So what is the logic followed in the construction of Huffman tree? Okay. So now begin with a set of leaf nodes. Begin with a set of leaf nodes. The same process, I have it in the next slide. I just showed. Begin with a set of leaf nodes. Okay, there is a set in the first line. And you have a leaf nodes, A, B, C, D. These are all the symbols which may occur in my message. Okay, and this symbol along with the frequency. If you take a set, A is occurring 8 times, B is occurring 3 times, C is occurring 1 time, etc. Okay, so this is the initial set. Okay, and now from this, we are going to construct the Huffman tree. So what we have to do is, now find 2 leaves with the lowest weight and then merge it. So now I'm going from left to right. Okay, so the frequency is 8, 3, 1, 1, 1. So 1 is the lowest frequency. So I will merge it. So C and D will be merged. Okay, after merging, and again, I will just go on from left to right, and E and F I can merge. Okay, then G and H I can merge. So whenever I am merging, the sum of the weight also I am accompanying in the same set. So GH, the weight is 2. So now once again, A is 8 times, B is 3 times, and C and D is 2 times, etc. etc. Now you pick up what is the next lowest. Next lowest is 2. You can combine CD and EF or EF and GH. EF and GH. Here in this example, EF and GH are merged. And what is the sum? 2 plus 2, it is 4. And then CD and EF, and then, 3. B is with 3 and CD with 2. So you merge it, BCD, and the weight is 3 plus 2, it is 5. And then 8, 5, 4. So the lowest one is 5 and 4. Merge it. Okay. So this is the way you have to proceed. This is the way you have to proceed. So, so if you look at the construction of a Huffman tree, what you need to do is, first of all, we will have an input set and then find out the lowest frequency set and merge it. This process has to be continued till all the nodes are combined or merged. Okay, So I think you have one important meeting at 10 o'clock. I have taken 2 minutes extra. Quickly, you have to join in that meeting. I will give you the link in the chat window. So it is compulsory for everyone to join. It is compulsory for everyone to join. And I'm just giving the link to join in the chat window. Just 1 minute. Students, can you see bit.ly link in the chat window? It is very important. You have to join. Everyone has to join. This is the instruction from the principal. Can you see the link?
Yes.
Yeah. So
Yes,
after
ma'am.
clicking on the link, you can leave the meeting now.
Okay, ma'am.